Good morning, everybody, and welcome to a new series of lectures. And this week we are going to talk about signal-based methods for fault diagnosis. So let us start with presenting the main ideas and some examples before going into details. So what does it mean to do signal-based fault diagnosis? So you may remember these slides that we have used many times to draw a parallel with medical diagnosis. During the last series of lectures, we explored change detection algorithms, which are ways to account for these two steps. So how to generate symptoms and how to evaluate them. And in particular, you remember that in this phase, we were implementing hypothesis testing. Today, instead, we are talking about methods to address the first two steps. So how to extract features from observations and how to generate symptoms, then later we evaluate. In this case, observations corresponds to time history of some measurement, so a signal, something over time. So over time, over discrete time, usually, we assume to have this signal. So I'm not drawing individual samples. The first thing that we need to do is to extract features. We had some examples in previous lectures about the features that we can extract. We can extract some rough features like peak values or average or minimum value, or we can have something more advanced like doing a Fourier analysis, for instance, of the signal. In general, let us say that what we are doing is to introduce a time window, a moving time window. Inside this time window, we are going to have n samples in general. And for every of these time window, we generate a feature. So even if this time window is of length n, for every time step in the signal, apart from the first n, we can have a window and generate a corresponding feature. Indeed, when we have a new measurement, we just move this window one time step forward. So in time, these features will be like this. So we have nothing here, nothing here, nothing here, but when we get to sample n, we have a first value. Then we have another value, and so on. So this is the sample number n. As soon as we have n of them, we can fill one window and generate one feature. We get a new sample, we move the window by one step, and we generate another feature. So this is quite general, and you also can consider the case where n equal to 1. This is still possible. So if we do that, basically, our features are just the raw observations or some transformation applied to single samples. Having a window of a non-trivial length is more interesting because you can do things like frequency analysis or noise reduction or other transformations that are useful because symptoms we are looking for may be easier to detect on transformed data with respect to raw data. Anyway, in order to provide a motivation for the need to do some transformation to extract features rather than look at raw data, I'm going to present you a simple example that you can actually hear. In this example, we show two audio recordings, one that is healthy and one that is faulty. So here you have a plot over time of the amplitude of the audio signal. So if you look at these two sound waves here, well, at least to me, they look the same. So there is nothing obvious that I can detect if I look just at the signal. If I look at individual samples, they look pretty much the same. So this part here is the same as here, as well as all the other parts. I don't see much difference. But the difference between these two signals will be quite noticeable to you when you hear them. So let us play them. Let us play the first one. And now let us play the second one and watch out for the difference. So I guess that everybody was able to hear something wrong with the second sound wave. But what exactly was that? Well, now the need for transforming data will become apparent. So let us show here what is called spectrogram. So the result of doing short-time Fourier transform on data. So if you don't know what short-time Fourier transform is doing, let's go back a couple of slides to here. Short-time Fourier transform is taking windows of data, and for every window is computing the Fourier transform. The Fourier transform of this window itself is a complex signal of length n. And in the plot you have seen, for every time instant, so for every vertical position here, the Fourier transform is plotted as this column of data here. Indeed, we get a two-dimensional result. So for every time step, so for a vector of time step, we have a vector of Fourier transform data. And the way to visualize it is using false colors. In these false colors, we see the amplitude of each component of the Fourier transform. So for each component of the vector you get doing Fourier transform, you compute the amplitude. So originally it is a complex value. You compute the amplitude of that, and you attach a color. So blue is small, and yellow is big. And so you see that normally, in a healthy signal, what we have are very noticeable harmonic components. And these should not be surprising because it is music. So we have the fundamental of the note that is being played. And then we have all the upper harmonics, and they're making up for the specific sound of each instrument. So each instrument has a different distribution of harmonics. And this is how actually our hearing system is recognizing different sounds. Our hearing system is not looking at the instantaneous value of sound pressure, but it is doing Fourier transform in real time. The nice thing, you can look up how the inner part of your ears are working. Fourier transform here is done mechanically. So there is one part that is called cochlea that has a membrane with different thickness, and every part of the membrane is a sort of bandpass filter resonating to a specific band. So where it is thicker, it is resonating with lower frequency. When it is thinner, it is resonating at higher frequencies. So we have a lot of nerves that are detecting which part of this membrane is resonating, and so you're doing this. You're doing Fourier transform over time. This is what your hearing system is doing. And this is why your hearing system was able to catch up at the fault easily. And the fault that now we can see, thanks to this plot, is this. So you see, in the faulty signal, there was an extra tone, a pure sinusoidal component that was applied during this part and this part of the signal. So we didn't apply it during the pause, because otherwise it would have been easy to spot even in the time plot. But in the time plot, when we are applying this spurious signal in the middle of music, well, you don't see anything. But in the Fourier transform domain, it is trivial to see that something is wrong here, and it would also be trivial some way to detect it. What we can do to detect it? Well, an idea is, let us take a slice of this. So let us look at a given time instant, and we can plot the Fourier transform. So we take the colors that we have here and we convert them back to a normal plot. So now let me put the frequency axis horizontally, and the magnitude it is here. So normally, if you look at the same slice in the healthy signal, we have a number of peaks corresponding to each harmonic. So I will not draw all of them. I will just draw a few of them. So we have the fundamental, upper harmonic, and so on, and so on, and so on, and so on. But when we have a fault, we have something in between that is quite big and shouldn't be there. So a way of detecting this is, first, to have a knowledge of what is the nominal behavior, and then we can simply compute the difference between what we get here and the nominal, and then this peak at this frequency will stand out immediately. So what we can do is to have a threshold for this frequency component. So threshold can be something like that. So normally you allow to have sound amplitude at this frequency, but here you know you need to have silence or just background noise. So you can have a threshold that is built like this. It is a sort of gate that allows everything in this band that is allowed, this band that is allowed, but here we know we shouldn't have signal. We know we can have some background noise, so here the threshold is not going exactly to 0, but this peak here is going to be detected. So this is a threshold on the actual signal, not on the difference between the signal and the nominal, but you can also do on the difference. So it is going to be just everything shift down in these bands, and here should be the same. So this was an example on a signal that you can hear, but we can also look at an example about a signal that you can see. So let us play this video. Okay, I guess that everybody was able to notice what was wrong in this signal. So the fault was something occurring on the camera as a sensor and was, well, not really a fault of the camera itself. But anyway, the end result is that we didn't have signal anymore on a big portion of the image. And so let us imagine if you want to build a self-driving car. This is going to be quite an issue. But luckily, they found a way to cope with that. And this is how they are doing it. I guess that these two examples were quite intuitive, and I hope that you got the feeling of what it does mean to do signal-based diagnosis. But I suggest that you try yourself to write an algorithm or a pseudo-algorithm for detecting the two faults that we have just introduced, and especially detecting the mud spot on the lens of the camera can be less trivial than what you can think. So I'm really curious about which kind of solutions you can come up with. So if you look on the book by Iserman, you can find this figure that is a taxonomy of signal and model-based fault detection. Well, actually, this is really funny how they call it, because I would say this is a taxonomy of signal-based fault detection. And here, methods are divided according to the kind of signal you are considering. So you have methods for signals that are periodic, like the music sound wave, that at least locally it is periodic. Or if you look at stochastic signals, or you can look at non-stationary signals. And if you look at the approaches that you see here, they are indeed approaches for generating features and symptoms. They are not yet complete approaches for doing also the last step, this symptom evaluation step. Because you see here, we have bandpass filtering and Fourier analysis. They are both approaches for detecting issues like the one we had in the musical example. Parametric spectral estimation is another approach where instead of computing the spectrum, you are estimating a model of the spectrum that is parametric. And correlation analysis is quite a similar approach because computing the correlation between two signals, that is the cross correlation, or the correlation of the signal, the autocorrelation, involves computing a convolution over time. But a convolution over time corresponds to a product of spectra in the frequency domain. When you come to stochastic signals, indeed correlation analysis is one approach, estimation of a model is another approach, analyzing the spectrum is another approach. And when you come to non-stationary signals, the short time Fourier analysis that we have shown in the musical example is an approach. So if you look at the musical signal, not locally, but if you look at the entire signal, well, then it is a non-stationary signal. Only if you're looking at a tiny portion of the signal that is a single musical note, then we have a periodic signal. And finally, an approach that is similar to the short time Fourier analysis is the wavelet analysis. But still, what they are doing is to compute features. So out of all these approaches, you have features. So you have yet to transform them into symptoms and then apply a symptom evaluation method. So let us start now with presenting some approaches that can work in the time domain. So actually, we already know about them because everything that we presented in previous lecture about change detection algorithms, they can easily apply as they are to signals over the time domain. And you can either apply them to instantaneous raw values, which means that your features, the one that you extract, are actually raw values, so there is no processing. Or you can apply them to some evaluation function. So we use the term evaluation function to express the function that we need to apply to raw values in order to generate features. But actually, you can generate features and then further transform them with another evaluation function. You can, for instance, take a signal that is very noisy, and then you can take a window of data and you can apply some denoising, and then you get another signal that now is going to be our features, which is the same signal as before, but for instance low pass filtered, so much less noise. And then on this one you can apply again the same. So you can apply another, you can find another time window, and then you can compute some statistics, mean and variance, for instance. And then you apply one of the change detection algorithm that we have seen in the previous lecture. Other kind of transformation that you can do is to do bandpass filtering. So let us assume that you know that default is going to appear as a signal in a given frequency band. So pretty much like the musical example. Let us make an entire new example. So normally your signal is like that, but at some point the fault is introducing a noticeable component at a given frequency. That is going to be then a sinusoid on top of our signal, and then it goes away. If we can apply over a time window of data, like here or here, a bandpass filter that is matched to this frequency, what we get as, in this case, features is another signal that is normally small here, but when we have the fault, it becomes big, and then it goes away. So this would be the result of applying a bandpass filter to this signal, where the band is tuned to this faulty signal we have here. Anyway, doing bandpass filtering is another way of doing Fourier analysis. Other two interesting approaches are computing cross-correlation and autocorrelation. So what does it mean? So let us assume that instead of knowing that the fault is a single component that is a pure sinusoid, we know that the fault has a specific fingerprint. Something like this. You were able to record examples of the fault, and the fault has this very specific behavior. If you want to look for this in a signal, the way to do that is by computing the cross-correlation between the fingerprint of the fault and your signal. Let us assume the signal is like this. You have your signal that can change, get big, and so on. But at some point, you have the fault happening on top of your complex signal. If you take the cross correlation between this signal and this signal, what you get is pretty much like this. So when the signal is normal, if the signal itself is not similar to the faulty signal, the result of the cross correlation is small, but here we have a peak. When indeed there is a part of the wave, the signal here, that is matching the example that you have for the faulty signal, you get a peak in the cross correlation. And then you can simply have a fixed threshold for this to detect this. And this is an approach that is used a lot in signal-based diagnosis, for instance, for vibration or noise analysis in engines or other machines where it would be really difficult to come up with a mathematical model of the dynamics leading to this fault, but it is really, really easy to get a recording of the fault. And when the fault is presenting, it is always presenting in the same way. So it is just a matter of pattern recognition. And cross-correlation is actually doing that. And finally, autocorrelation is a cross-correlation of the signal with itself. Why should we need that? Well, the autocorrelation of a signal is defined in this way. So you see, you have here the convolution of the signal with itself, and you are computing it over a time period from 0 to some t. You average over the length of t, and then you take the limit for t that is going to infinite. So when you are taking the limit that is going to infinite, t is no longer a parameter here. So no matter what, so the only thing that is a parameter here is tau. This tau here is indeed in the definition of the autocorrelation. So what does it mean here? It means that you are looking at the behavior of the signal at a given point in time versus the behavior of the signal delayed by the value tau for all possible values of t. So if you have a signal that is pure noise, if it is a white noise, let us try to draw a noise signal. So I'm not very good, but if you compute now the autocorrelation, what you get? You get that for tau equal to 0, you have y of t that multiplies y of t. This is integrated. And this is giving you the energy of the system, because you integrate yt squared over all the possible values of t. This is the energy of your signal. And this is always different than 0. But if your signal is a true noise, if it is a white noise, you know from the definition of white noise that the autocorrelation at time instants that are different is 0. So the value of the signal at a given time is completely independent of the value of the signal at another time. So the autocorrelation of a white noise turns out to be a Dirac delta in 0, and then you have nothing here. So this is tau, and this is the autocorrelation RYY. So if you know that normally there is nothing special in your signal, there is just noise, so the normal behavior of your machine is just to make some noise. So you have your engine rotating and you have some very low volume humming that is pretty much going to be a white noise. This is the normal situation. How to detect this is actually the normal situation and no fault is present, you compute the autocorrelation. If you get an autocorrelation like this, you say, okay, there is just noise, and for me, this corresponds to normal behavior. But now let us assume that there is a faulty behavior in your engine, and this faulty behavior is leading to some periodicity in the signal. So maybe every rotation of the engine there is a clank or some other noise. But, well, in this case, you don't know what is the speed of the engine, so you don't know what is the periodicity. But you just expect that a fault is adding some periodicity in the signal. So for instance, it could be that the fault is presenting like a peak in the signal now, and then another peak in the signal, and then so on. And this is going to be periodic. How can you detect periodicity in a signal? Well, indeed, the autocorrelation is the way of doing that. So if you have a distance between these two peaks in time that is equal to, let's denote it by tau star. Okay, when you have a periodic spurious signal on top of this and you compute the autocorrelation, no wonder you get a peak here, exactly for tau star. So, if you suspect that the fault is leading to some periodic behavior in the signal, you just compute the autocorrelation and you look at peaks that are not in 0. And this is an indication of the fault. And this is an example for a signal that instead is clearly periodic. So you have the sign of this term here, and this is the angular velocity, omega. So it means that you have something like this. You have simply a sinusoid, and the autocorrelation is going to be a cosinusoid. So you start high, and you see the argument of the cosinusoid is omega, the angular speed here, that multiplies tau. But remember that omega is equal to 2 pi over the period. So let us call by tau v the period. So it means that when you look at the autocorrelation signal and you look at the value of tau that is equal to tau v, the period. So let us assume we draw it here. We get a peak because you know that if tau is equal to tau v, so this is simplifying with this, you get only 2 pi. So you have the cosine of 2 pi. The cosine of 2 pi is 1. So you have another peak here. But you have also peaks for every value of tau that is a multiple, an integer multiple of the period. And this makes sense. And this is going to happen also in this case here. So if you have a signal that has a period equal to tau star, it is also having a period equal to 2 times tau star, 3 times tau star, and so on. So you have multiple peaks in your autocorrelation signal. Anyway, once you have your autocorrelation signal, you can derive a threshold that is big around 0, because you know that around 0 your signal is always correlated, but is small for other values, such that when you have a peak, a red peak like this one, it is crossing the threshold. Okay, so let us move to frequency analysis now, considering that these last methods that I have shown to you are basically equivalent to things that we can do in the frequency domain. So let us recall again that we are looking at this chain of computations, and we have raw data, and here in this step, the feature extraction, we are doing our Fourier transform. And later we are looking in the frequency domain at frequency components to generate symptoms and to evaluate them. A typical example for applying frequency analysis methods for fault diagnosis is for signals that are periodic and stationary. And this occurs a lot for rotating machines like pumps, turbines, engines that are operating in constant conditions. So constant speed and constant loading. And this is an example showing what happens for this kind of pump. We see here the internal components of the pump, and in particular we have the bearings, and in this case we have 7 steel balls. So if F0 is the frequency corresponding to rotation of the bearings, we may expect a harmonics at 7 times F0. But the bearings are not the only one. So we see that we have here the gears. So for every teeth in the gear mesh, we have an impact. So if we have n teeth, we are expecting another component at n F0, and so on for the screws, for instance. So indeed, if you can take vibration or sound measurements of a rotating machine, you expect that there is some baseline normal pattern in the frequency domain where you have a main component corresponding to the rotation speed of the machine and other components that are corresponding to the rotation speed or of other axles that you can have in the machine. But everything else should not be there. And if you see components that are not matching those harmonics that you expect, they can be an indication of a physical damage. Because indeed, when you have a rotating machine, an axle that is damaged, well, this is introducing some higher frequency components, as we can see in this example. Here we see the case of a single shaft. Due to eccentricity, when the shaft starts turning and we look at the signal of the displacement, we see that for every rotation we have one period of a sinusoid. So that's a pure sinusoid and we have nothing else. Here again, another view of the same phenomenon. So for a shaft that is perfectly circular, but its rotation is eccentric, if we look at the displacement, as we said, we have a sinusoid. So every point on the
circumference of the shaft is causing one point in this sinusoidal signal. And if we look at the spectrum of these, we see a single clear spectral line corresponding to this harmonic frequency. This fundamental frequency. But now we can move to a different case, the one of a gear that has some damage on a tooth. So now the profile of the gear is no longer a perfect circumference. So we normally have some spectral lines because we have extra harmonic components. But you see how the damage is introducing a loss of regularity. And so this damage itself is causing some spurious line in the spectrum. So we could have predicted the spectral lines due to the gear mesh, but this damage is introducing a new one. And this is something that we can use to detect this kind of damage.
So in the case of a machine that has different components that are rotating and possibly at different speeds because you have gears in between, then every single one will have a characteristic spectrum, a fingerprint denoting normal behavior. And if you can take acceleration, vibration, or sound measurements close to each component, you can check whether the nominal fingerprint is present there in the frequency domain or not. And this allows you not only to detect faults, but also to isolate the specific component of the machine that is faulty. And in the industry, there is a long tradition of applying these methods that are very well developed, but they anyway suffer from one drawback. That is one drawback that, as we said, is common to signal-based methods. So they are developed for stationary conditions, for conditions where you have a lot of data characterizing the normal behavior. When you have transience conditions, then it is much more difficult to apply them because when you have transient conditions, if you look at the spectrum, it is no longer something constant like we expected. So if we look again at the musical example, you see that while a note is played, we are in a stationary condition. So we have a given frequency for the fundamental component, the one that corresponds to that note, and the upper components. But if instead of a musical signal, this was the signal out of a machine with different rotating components operating in stationary conditions, okay, we expect something similar. But when the machine is speeding up or down, all these frequencies are increasing or decreasing. So this component here, during a speed up, will do this. And during a speed down, will do this. So the entire spectrum will be shifted up and down when you have a change in speed. You can overcome this drawback if you know the speed of your machine, and then you compensate for that. So instead of looking at the spectrum for a given component in frequency domain, look at that for a given speed of rotation. And then if you normalize by the speed of rotation, then this is going to be flat again. But when you have more complex transients, where not only the speed is changing, but also the loading of the machine is changing, well, applying a signal-based method becomes quite difficult. From a mathematical point of view, the frequency analysis is defined by introducing the Fourier transform, which I presume you already know about. So we are taking a signal y over time, we apply the transform, and we get a capital Y over frequency. The short time Fourier transform is obtained from this one by multiplying the signal by a moving window. So this function, omega, is a window that is a signal that is a sort of a door. If we define the term tau here, the function omega w of t minus tau is going to be something like this. It is 0, then it is 1, then it is 0. So this is implementing a rectangular gate function around tau. If you move tau, this is moving around. So if you multiply this signal, the window that is either 0 or 1 by your signal, this is a way of selecting only the portion of the signal that is inside this gate. And it is not mandatory to have this shape. Actually, most of the windows that are used for the short-time Fourier transform are not like this, because they are introducing some artifacts, so are more smooth, like, for instance, the Hamming or Hanning windows. They are smooth. Anyway, once you do that, you take the Fourier transform. And now you get a signal that we say is two-dimensional because it is indexed over frequency and indexed over tau, so the time offset. Another approach that is similar because it is producing a two-dimensional output over frequency and over time is the wavelet analysis. This is a sort of generalization of the Fourier transform. In the Fourier transform, the basis functions that you are using are sinusoids and cosinusoids, but in the wavelet analysis, the basis signal are arbitrary, and they are what are called indeed wavelets. And finally, you can take the spectrum of a signal and do some processing on that. And for instance, you can get what is called the power cepstrum. So you take this logarithm of the magnitude of the spectrum, and then you take the inverse Fourier transform. And why it is useful? Because it turns out that if you have signals that are convoluted, like you have your signal that is going through a filter, the power cepstrum is returning you sums of the cepstra of the individual signals. That is your signal and the impulse response of the filter in this case. And so this is why this is happening, because we know that convolution in time domain is equal to product in frequency domain. So if we take the logarithm of these, then we are separating the product of the signal spectrum and the filter response into a sum. And then when we take this inverse, then we get the sum of the cepstra. And then it is easy to do a linear separation. So why this can be useful? So consider the case where the fault corresponds to some filtering applied to your system. So you can have a microphone, for instance, and you know that when there is some mechanical failure in the microphone, the effect is that the output of the microphone is low pass filtered. Well, you can detect this by computing then the cepstrum, because if you know what is the Fourier transform of what is the response in the frequency domain of the filter, then here you're going to easily separate that from the spectrum of the signal. And the signal is arbitrary, so you don't know in advance what is the spectrum of the signal. So this is the usefulness of the cepstrum. So it allows you to do linear separation in the frequency domain easily. Anyway, whatever method you are using, please remember that we are just generating features and symptoms. At some point, we need to add the missing ingredient, that is the symptom evaluation. So we need to apply at the end some change detection algorithm, which is going to be applied, for instance, in the case of the frequency analysis, to components of a spectrum. So we need to know some deterministic or statistic description of what is the normal behavior of those spectral components. So all the methods that we have seen in the previous lecture can then be applied. What is different is just the way we generate features and symptoms.